I'm on the turkey team. I'm not. But yeah. Oh, come on. Hey, people. So, uh, camera up. All, all good. Yeah. Questions about the homework, needed hints, clarification. Everybody good with the homework? Uh, modulo that you need more time, you made it. Yeah.
For number 4 with the dot product, or the vector, trying to find a point that maximizes the dot product, do we have to worry? I guess I'm assuming it's general position, correct?
Yeah, otherwise one of the points that maximizes it.
So it's like what about like an edge case where like a point's very far off, but it's super long, such that the dot product is greater than a point that's actually closer to the vector? Do you get what I'm saying?
Yes, but if you remember what a LP is saying, the reason that this whole P algorithm works, big hint is that I have my feasible region in general LP. Let's go over the LP. That would be my feasible region, what we called C of n, the feasible region of the intersection of every point. And once I told you what is a small c vector, the cost vector, so that would be capital C. That small c, once I told you the direction of the vector, it just tells me go in this direction. That's where the wind pushes you, and the more you'll go in this direction, the better it will be. Or alternative, or equivalently, if once I know this direction and I don't care at all where is the origin of the axis, the origin might be here or here, I don't care. Once I have this direction and I look at any line that is orthogonal to C, we're talking about question 4 and C, but it's also very, very relevant to what we are discussing today. Once somebody told me where is a force, pushes me where the gravity pushes me, then every line that is orthogonal to C, or to 2D, it would be every plane that is orthogonal to C, 2 points on this line give me exactly the same revenue. So if I have P1 and P2 on this line, and they're parallel, I don't know that they are the optimal one, but since they are both on this line and this line is orthogonal to, and this line L is orthogonal 90 degrees to C, then P1 times C equals P2 times C. I have the same revenue. So where is the origin is irrelevant. I know it sounds a bit counterintuitive that some vectors are original. If I make C much longer, I didn't change anything. Of course, my revenue changed, but 2 points, if 1 point beats the other in given C, now I have P3 that is better than P1 and P2. Then as long as C points in the same direction, no matter how long or short it is, P3 will be better than P1 or P2. Better than P1 and better than P2. And P1 and P2 have the same revenue. So we mentioned quickly the linear programming algorithm that we mentioned last time. We are adding the half planes one by one, H1, H2, H3. At each point, we keep Vi minus 1, which is the optimum of all the planes we had so far. And we have now age I, the next half planes. If it doesn't violate Vi minus 1, then it's still the optimum. If Vi minus 1 is just Vi. If it does violate, then we are computing a new optimum, but only on the blind plane itself. That was a pretty big theorem that guaranteed it, because if it's just floating inside Hi, then we can improve it by going to the boundary of Hi. And we can use this lower dimension search only after we checked if there is a violation. If there is no violation, then I'm not sure that the new optimum is on Li, the boundary of Hi itself. Example, here is Hi plus 1. It doesn't violate Vi. And of course, it's completely redundant. It doesn't even matter to the polygon. And why did we argue that it's expected linear time? Help?
Because there are only two half planes instead of general position that define the optimum. So on the average case, statistically,
Yeah,
like the
that,
half plane doesn't matter.
look that we are doing the following mental step. At the ice step, and let's say that I already know what are the half planes that participate. You see all the half planes. What you don't know is the order. Out of all the possible orders of this particular half planes, what is the chance that now my new optimum, Vi plus 1, is the red point, Vi? What's the probability that the last half planes that I added is one of the two that determines Vi? Answer, the probability that Vi is not Vi minus 1, that is that I had to improve something, is 2 over I. And in 3 dimensions, that in 3 dimensions, this probability will be a vertex of the polytope is determined by 3 half planes. So it's 3 over I. Now, if, and of course, in D dimensions, is D over A. And now, what is there for what do I do in the 3D case if I have a violation? I call the 2D case. And we start from scratch. And then what is the probability that at this case, what is expected work? Well, let's nail down the expected work. For 2 dimension, the expected work at one step expected work is 1 for sure, just to check, plus with probability of 2 over I need to call the 1D linear programming. That's what I do if there is a violation. That takes a constant that I'll ignore times I, if I have I half planes. So the expected work is only 3. What do I do in this case? Expected work in 3D the expected work is 1 just to check if there is violation, plus with probability of 3 over I need to call the 1D LP that takes about, whose running is about 2 times I. And in the D dimensions, for the same reasons, I have probability of D over I times D minus 1 over I times dot, 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 up to 1. So the expected work, and I'm jumping a few steps, expected work per one step is order of D factorial. So we suffer from the dimensionality. But that's for one step, adding 1 new half planes. And the total work, total expected work, is therefore theta of D factorial n. But D factorial meaning 1 times 2 times 3 times dot, 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 D. So if dimension starts to be large, maybe you don't want to use this algorithm. Use simplex instead. If D is small, you have a linear time algorithm. I mean, it's still linear time algorithm the moment that the dimension is fixed, but that's as long as the dimension, remember, dimension is a number of variables, not to be confused with n, which is a number of constraints. So it likes to take a lot of constraints. It doesn't like to take a lot of dimensions. And there are variants that shows at least sub-exponential, depends on the dimension, but it's more interesting theoretically, less so practically. So what I'm going to do today, and maybe we'll spill to next class, probably to next class, is leaving a bit computational geometry and talks about what else can we do with LP. LP is a big tool, and ILP is a very big tool. Once you're familiar with this, there is a million problems that you can solve by finding a library that solves linear programming or integer linear programming, and phrase your problem as an LP/ILP. And I'll show a bunch of such problems, and some are quite surprising. And when I'm saying phrase it as a problem, you're going to say MATLAB, Python, anything that can talk to one of the libraries. One of the famous libraries is simplex that I'll mention in a second. And you just said, here is a matrix, my constraints. Here is a vector of variables. Here is a vector of the upper bounds, lower bounds. And from this part, which variables do I want as integers? And the ILP will give you a vector in return, and it's up to you to understand what this vector corresponds to in the original problem that you started from. It all sounds very, very abstract in the air at this point. Hopefully, after a few examples, it will make sense. So, linear programming in dimension D, once again. C is a vector. I want to find a point x. Vector x, which consists of several d components, x1 dot 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 xd. don't confuse, x is a vector. It has x, y, x, y, z, x, y, z, w. C is my cost direction, and I want to find the point x that minimizes c times x. If I want to minimize it, c times x. If I want to maximize it, it's minus c times x. With the following constraints. A1 vector given to you, dot product x is smaller or equal than B1. What does this constraint tells us? These are all the points. We talked about it, that here is the vector A1 vector. And I have some point on the line L1. This is one point P. And I'm looking at all the point A1x, such that A1x is larger or equal than A1 times P, some constant. All the points on one side of the line corresponding to it, or the half space, or inside the half plane, half space, half hyperspace, and so on. So this is what this constraint implies. And another constraint, remember in the diet, each constraint was one type of vitamin. In matrix multiplication, what do? I take the vector A1, write it as a row vector, taking A2, taking it as a row vector, all the way up to AN. Here is a vector X. So this matrix M dot product X is smaller or equal than yet another vector B1 dot 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 Bn, meaning A1x smaller or equal than B1 AN x smaller or equal than Bn. Just writing everything in this way. And sorry, this matrix is A, not N, in this slide. Make sense? And if you want to write it's actually larger or equal than B1, then as usual multiply both sides by -1, and the smaller or equal flip its direction. If you want to write it's actually equal to, just on the hyperplanes, then you're adding two constraints, one that it's smaller or equal, one that it's larger or equal, meaning that exactly on the half plane. That's like why this is a canonical way to write integer linear programming. And the simplex algorithm, that you need a bit more linear algebra that I didn't want to assume that you have, so I don't describe the algorithm itself, said I'll start from one vector in the feasible region, and I'll follow gradient descent from one vector to the next vector, from one vertex, to a next vertex, to the next vertex. Here it is. Here is my polytope, starting from one vertex, following an edge to, starting from one vertex, following an edge to a better vertex, a better vertex, a better vertex, until I find a vertex that is a minimum locally. And if it's a minimum locally and it's convex polytope always, then it's also the global optimum, as usual. So that's the beauty of convex programming. And if you need it, here is one of the libraries that has thousands and thousands of years, supported by IBM. It was a company that IBM bought and keep working on it, that optimize. It's not the only one. For some application you need to pay, for some application as a student. You can use, mostly as students, you can use, and that runs really fast for unbelievable amount of variables and dimensions. Simplex, just once you express a problem as a linear programming, considered it solved, no matter how large it is. Okay, and it practically, it's not in theoretical bounds, but practically that's a rule of thumb of linear programming. Again, no matter how large a problem is, 10,000, 100,000 variables, many dimensions, consider it solved once you express the problem as linear programming. What is ILP? ILP is the very same thing, just an LP, 2 dimensions, higher dimensions, whatever, except that I can specify that integer linear programming, where is it? I lost it. I can specify that possibly all the xi's, possibly some of the xi's up to me, must be integers. I don't want any float values for some of them. I want them to be integers. Does it make the problem slower? Yeah, it can run much, much slower. Does it mean that I can solve more problems? You don't see it obviously why it's so much stronger, but it will make it extremely useful to solve a lot of problems, including NP hard problems, which otherwise you're pretty lost in trying to find optimum solution. In ILP, like Cplex, once it gives you a solution, you're guaranteed that this is the optimum solution. Like, it's not approximation, it's not anything else, it is the optimum one. And so here's my xy. Here's one half plane. And here is another half plane. This point is 1, 2, 3. 1, 2, all the way to 100. So the point 101, this point, 1, 100, is an integer point. The 2 half planes does not contain 0, 0. Does not contain 0, 0. But it does contain, what called it, the 0 and 0, 0.1. This point, 0, 0.1. So what is the solution of the LP? I need to tell you what's the cost function, of course. So as usual, I'll assume that the cost function points downward. C points downward. What is the solution of the LP problem? That's, I can tell you these 2 half planes looks like so. Contain this, so they are this very thin sliver. Solution to the LP, this vertex right here, when I'm looking for the lowermost point. Solution to the ILP, the lowest point, which is integer out there, 100 over here. Whatever. So the way I build it, 0, 0 is not inside it, no point until I got to x equal 1, and that's the lowest one. So solution to the LP and solution to the ILP can be quite far away from each other. Like, there is no guarantee that one is a good approximation to the other, but in many cases it is, and you are happy when it is. And sometimes ILP can run quite slow, so you'll use LP as your first guesstimate. Okay, I think that I just said it again, just a few libraries, etc. I'm pretty much returning what I said in the previous slide. An ILP, of course, if it's NP hard, you cannot express that you'll always run fast. So why do I tell, if I don't expect it to run fast as an ILP, if I solved an NP hard problem, why do I teach you? Why do I say that it's useful? Because it will not run fast, but it probably run much faster than everything that heuristics that you'll try, no matter what's the problem. Why do I think so? That the ILP will run faster than what you will implement otherwise is because all the thousands of years of work that are invested in optimizing the ILP. Okay, so you assume that ILP will do a very decent job if possible. Not always, not necessarily, but it has better chance to run reasonably fast comparing to other things that you can try. So now I want to tell you that there are some problems that we can express as LP or ILP, and some that are taken from very different domains. So as I said, I'm leaving the hardcode material of computational geometry for these meetings. Let's talk about bipartite matching. That by itself is not a very hard problem. I have a graph. It's bipartite because every edge connects one vertex of A to one vertex of V. Let's say it's possible every edge of this graph could be an assignment of an instructor to a subject. And I want every subject to be taught by a single instructor and every instructor to teach only a single course. So that's why we'll call such. And I want to have as many subjects as possible, or every instructor and every subject to be taught. Not every instructor, not every topic can be taught by any instructor. Like this topic can be taught by this instructor and this instructor and this instructor. This topic can be taught only by this instructor, so when I'm deciding what this instructor will teach, it's either this or this, but not both. So I'm looking for a one-to-one matching here, where every person or every node is matched, but matched meaning you're only on one edge. And edges can be picked, of course, only from the subset I showed you. But we said not every instructor can teach every course, and so on. So having an edge meaning it's potential teaching. How do I decide whom is whom? Another story, more outdated, that males, females, that said they know each other, and now you need to arrange marriages only in this bit, which is bipartite marriages, and it needs to be one-to-one. Okay, so yeah. And I want to have as many edges as possible. So you see here a matching. I picked a subset of the edges. It's not the maximal cardinality matching, right? I could have added more edge, presumably. But at least it is, the red ones are matchings, constitute a matching. They are edges of the original graph. Any questions about the definition of the problem? Okay, and max cardinality matching in bipartite graph, it's a very classical problem, and there is polynomial time algorithms that can solve it actually quite fast. What about matching in a non-bipartite graph? There are polynomial algorithms also for non-bipartite graphs to find a matching, again, set of edges so that every vertex is adjacent only to one edge. But they are polynomial, but they are much more complicated to implement and are slower. What happens if my cost function is a bit different? Like there are some pair of edges that I don't tolerate together. There is some fancy pricing. I'm very fast exceeds from the set of problems that I have known that there is polynomial time algorithms to solve. On the other hand, let's express the whole thing as an ILP problem. So when I specified an ILP problem, I will specify a lot of variables. Namely, for every edge of the graph, I'll specify a variable. I'll call for an edge E, x sub E is a variable associated to this edge. So the number of dimensions here is the number of edges in the graph. Probably not 2 dimensions or 3 dimensions, but much higher dimensions. Now, I will say that xe must be Boolean. How do I force it to be Boolean? I will say its value is, oh, sorry, it's x sub e here. Keep forgetting to fix it. At x sub e for every edge e is bounded by 0 and 1. And oh, by the way, it needs to be integer. How many integers do we have between 0 and 1? Either 0 or 1. Now I need to say, how is this related to my original problem? My understanding will be if xi is 1, it means that E will participate in a matching that I'm looking for. And if X is 0, then X is not participate. Quick example. Please tell Martin to replace the whiteboard. I did multiple times. So here are my 4 variables, because I have 4 edges in this graph. And I want to use as many edges as possible. I want to use as many edges as possible. So my cost function would be maximize x1 plus x2 plus x3 plus x4. How can so far my solution is take every xi to be infinity. My next set of constraints is xi is between 0 and 1 for each variable I equals 1, 2, 4. So my solution is not infinity to this cost function. It will be all the xi's are 1. So my cost function would be 4. My next constraints, let's read the next constraint, is that I'm meditating on A1. A1 is connected to x1 and x2. x1 plus x2 smaller or equals than 1. That will make sure that A1 is in a monogamous relationship. It's either married B1 or B2, but cannot marry both. And similarly for A2, A2 connected to x3 plus x4, smaller or equals than 1. I'm good with the A's. Now for the B's. For B1, x1 plus x3 smaller or equals than 1. And for B4, B2, x2 plus x4 small or equal than 1. And I said that I required monogamous relationship here, but I can run the LP to this problem, and it's quite likely that the solution to this problem would be, look at all these constraints, would be 0.5, 0.5, 0.5, and 0.5. Each edge, so xi equals 0.5 for each one of the i's. So interpret it as a matching, then you'll understand what it's half and half married to. Yeah, so it's fine. It solves my problem. That's what I'll get had I run linear programming. If I forget about the I. Now I also ask that each one of these variables will be an integer. Again, between 0 and 1. And now suddenly the half, 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 half doesn't hold anymore. So a possible solution would be take these two edges, that would be one possible solution, and the two diagonals would be another solution, and you'll get either this one or this one. Again, why do I teach it to you despite having so many polynomial algorithms for matching? Because you can change many more things. The graph is non-bipartite. Who cares? Everything is still the same constraint, the same everything. Make sense? So much more flexible. So vertex cover doesn't have polynomial algorithm, actually. It's one of the famous NP-hard problems. So what is a vertex cover problem? I'll give you a graph. And I want to pick subset of vertices so that every edge is hit by one of the vertices, at least one of the vertices that I pick. Do I have an animation? No. I don't have an animation. The time that I spent this semester fighting with this whiteboard. Yeah, so here is my graph. And I want to pick subset over the vertices so that, like, nails them so that every edge is at least have one nail. So solution one, pick all the vertices. Obviously, you hit all the edges. That will work, but I want to have as few vertices as possible. Solution two would be I can pick this vertex and this vertex and this and this. And think that and this one. That will work, but it's also not optimal. Optimal one makes sense that I'll pick this one, so I'm getting rid of almost all the edges. I still need one to cover this one. And this problem is famously NP-hard. Let's solve it with ILP. So xi, I'll have a variable for each one of the vertices. In the matching, I had a variable for each one of the edges. Now I have a variable xi for each one of the vertices of the graph. And as before, xi will be a Boolean variable. And if xi is 1, it means that the vertex vi will be in my vertex cover. And if xi is 0, then vi is not in the vertex cover. What are my constraints? I'll get to the cost function in a second. What's my constraint? Let's look at B6 and B5. In my solution, I want that x6 plus x5 would be at least 1. If it's 2, I'm fine with this. But it must be at least 1. Why? Because they are integers, so it cannot be. Here is an edge. To cover the whole graph, I must cover this edge, which means that either B6 or B5, or possibly both, will be in my cover. This will mean it cannot be that both these variables are both 0, which would mean that neither V6 nor V5 are in my cover. At least one of them must be in my cover. And I'll repeat similar inequality xi plus xj larger or equal than 1 for each one of the edges of the graph. So the dimension is number of vertices. Number of constraints is more or less the number of edges, plus that I'm saying that every vertex, every xi must be larger than 0 and smaller than 1. Cost function, minimize the number of vertices that you pick. Minimize the sum of the xi's, because that's exactly, in this summation, I sum all the n variables, but if the value of this cost function is just all the xi's that are 1, just their sum, the number of xi's that are 1, the number of vertices that I picked. Cool. So that's where the first example of where I'm using ILP to solve NP-hard question. So, yeah. Another example, art gallery. Remember, art gallery, we always need at least, we can always do with n over 3 vertices to guard the whole polygon. What is art gallery problem? It was a while ago. P1 sees the point Q if the segments between them is fully inside the polygon. But let's check a tendency today, just curiosity. I know it's holiday, etc. But let's have some evidence who was desperate enough to come today. Or serious enough for, you know. So, oh, sorry, didn't take the other side. That's it. Come on. Okay. So, P1 sees Q if the segment between them is fully inside the polygon. Pick a minimum subset of vertices so that I see the whole polygon. We'll have to talk about seeing the whole polygon. It will actually be a bit tricky. Let's instead say I have some discrete set of points that I want to see. For example, I want to see each other vertex. That would be an example of a discrete set. Okay, I need a discrete set of vertices that I'll say if I see all of them, maybe it's sufficient. If not, then we'll talk about it, but it will take more gymnastic otherwise. Okay, and as we discussed, it's NP-hard problem. Yeah, and so we need ILP. Just to remind everybody, couldn't avoid some GeoGebra involved. So here is my polygon, visibility of a guard, visibility from one point, visibility from another point. It's and so on. Worth mentioning is the common algorithm to solve the art gallery is try to go greedy. That is, find the guard that sees a maximum area, find the guard that sees a maximum area, and pick now the second guard that adds as much area that the first one did not see. Pick the third, so you're asking what is the area that the second one adds to the first one, what area that the third one adds to the first two, and so on. Just go greedily, and it's not bad if you want to capture as much area as you could. It can be less than optimal if you quite less than optimal, quite far from opt if you insist on covering the whole polygon. Okay, here is my polygon. There's the vertices 1, 2, 3, 4, 5, 6. I want to solve it with ILP. I'm going to pick a set of vertices so that every vertex is seen. If I'll pick V1 to be in my cover, in my set of guarding set, I'll put a camera on V1. It sees itself, by the way. So a vertex that I put a camera on it sees itself. But in addition, the visibility of vertex 6 consists of vertex 1 and 5 and 6. Vertex 6 sees itself, sees vertex 1, sees vertex 5, but it does not see vertex 3 because the segment between them is not inside the polygon. Right? Vertex 1 sees vertex 4, the segment between them is inside the polygon. So if I'll write what is a visibility polygon of vertex 1, it consists of vertex 4 as well as 1, 2, 5, and 6. These are all the vertices. So the only vertex that vertex 1 does not see is only vertex 3, obviously. So now so my first step to solve this problem with ILP is first to compute for every vertex what other vertices it sees. And now I'm ready to write my vertex 1. I'll think about vertex 1, and I want to say, in order to guarantee that vertex 1 is seen, then where can I place guard so vertex 1 is seen? I must place a guard either in vertex 1 because it sees itself, or I must place a vertex on 2, or on 4, on 5, or on 6. But if I'll play, yeah. So if I'll place a camera, a guard on vertex 3, it doesn't help me to see vertex 1. They don't see each other. So xi, as you guess, xi is 1 if and only if vertex I is picked. Xi 0, meaning vertex I is not picked. What are the constraints of who is the smallest one? What are the constraints for vertex 6? x1 plus x5 plus x6, 1. If it's 2 or 3, I'm happy. But if it's 0, it means that neither v1 nor v5 nor v6 were picked. So nobody sees vertex 6. I just look at the visibility region of vertex I and said sum up all the vertices in the visibility region, it must be at least 1. And I'll do it for each one of the vertices, and I solve the ILP. And that solves for me the art gallery modulus that all I need to see, all I guarantee to see, are only the vertices. So I can add more witness points, and require to see the more witness points. And practically, what we'll do is that I need too many witness points. So what I'll do is I'll solve the ILP with my original set. And now if I check if some subset of vertices that I pick sees the whole polygon. If they see the whole polygon, I'm happy. In this case, it will work. If they don't see the whole polygon, even though they see all the vertices, then I'll find the point Q that my original set of guards don't see. And I'll add the constraints for it. Also, the sum of vertices that see this one point Q also should be larger or equal than 1. And I solve the ILP once again. And I hope for good. Like, I hope that after a while, I would not find this witness point again. But it's not guaranteed to work. But it's as good as we can get. Here is another cute trick that I can get from back to vertex cover. So here's my problem of the vertex cover. Pick a subset of vertices that will cover everything, cover every edge. And here is a problem of the weighted vertex cover. Every vertex has a weight, how many dollars it cost me to use. If I'm going to use vertex, I, then I didn't say it explicitly, sorry, not in the text. If I'm going to use vertex I need to pay WI. Every vertex here comes with a different cost. How many dollars it costs you to place a base station there? If you think about it, I want to that can communicate with every edge along every street. Quite important, actually, in vehicle-to-vehicle transportation. I want every street to be connected to a traffic. I place some base station on traffic lights in the junction, and then vehicles to vehicles can establish using this extra network. So if these are the streets, I want to cover all my streets with my base station. I want as few base stations as possible. What the weights introduce here is that building a base station on B5 will cost $20. B6 will be much more expensive. And does it make the ILP significantly different? Not really. The constraints for every Vi and Vj, every edge in the graph, only pairs that are edges, xi plus xj should be larger or equal than 1. Just as before, every edge should be covered. And instead of minimize the cardinality, which is the sum of the xi's, now I minimize wi, the cost that for using vertex I, but times xi. So if I picked xi, I'm paying wi as part of my cost. If xi is 0, I don't need to pay for it. Now, is picking an approximation for the unweighted case? Is it easy to pick an approximation, a set that is not more than twice the optimum? It's very easy to pick factor 2 approximation, set of vertices that will give me that will give me at most twice the cardinality. The algorithm goes by pick an edge, pick both vertices of this edge, put both vertices in your cover. Again, I pick this edge. Opt will must use the optimum set must use either this one or this one. I'll pick both of these vertices. And once I pick both these vertices, I'll remove all the edges that are connected to them. And I'll keep iterating. So pick an edge, pick both its vertices, remove everything that you just covered. And that's a linear time algorithm, and because for every vertex of opt I used 2 vertices, it's at most twice the optimum. So this trick works very nicely for graphs that are for the unweighted case. Can I find a good approximation for the unweighted case? Unweighted case, for the weighted case, sorry. For the weighted case, this trick doesn't work because I might choose if this vertex cost $100, but this one cost only $1, and everything else cost only $1, then I may very much want to avoid this edge. And this approximation that I gave you doesn't care about the weight. So I need a bit more tricks. So here is my solution to solve the weighted case. It's exactly what we had in the last slide. The ILP would mean opt, to find the opt, minimize wi times xi, such that xi is between 0 and 1, an integer. Vi, vj, for every edge vi, vj in the graph, xi plus xj should be larger or equal than 1. And the set of vertices are just all the vertices that equal 1. That's the ILP. And maybe your graph is small enough, or the instance is small enough that ILP runs in a time that you are still alive and awake, so that will be fine. But maybe the ILP is too slow. Does it mean that everything is lost as far as approximation? Not really. Let's take this problem, the ILP problem, and erase the word integer from everywhere. So this is what's called the LP relaxation of the weighted vertex cover. That's the ILP. And here is the LP. I'm just using yi instead of xi because I want to refer to them differently. So I'm trying to minimize, my variables are y1 dot yn. Yi just tells me, do I pick vertex I or not? Except that here I don't force the yi to be integers. Everything else is the same. Yi must be between 0 and 1. Yi plus yj is larger or equal than 1 for every edge ij. and run the linear programming, not the integer linear programming, the linear programming. As I said, simplex linear programming, extremely fast in any case, excluding very extreme cases, but even the extreme cases with tiny bit noise will still run extremely fast. So I'm running the LP. What would be my constraint? I want to have a vertex cover only on this graph. So my constraint is minimize. I'll write the unweighted case. Minimize x1 plus x2 plus x3 subject to xi between 1 and 0. x1 plus x2 should be larger or equal than 1, meaning that either this vertex is picked or this vertex is picked, but x1 plus x2 is at least 1. Similarly, x1 plus x3 larger or equal than 1, and x2 plus x3 larger or equal than 1. And when I required it to be the ILP, then my solution for this graph will be what would be my value of the cost function. Not hard for this graph when it's ILP. 2. I must pick 2 vertices. I don't know which ones. What will be the solution for the LP? No. I need to assign. I see what you're saying. I need to pick value. What's the value of the cost function when it's a LP? I erase the word int from it. Everybody agrees? And this one is 1.3. So what it means that this plus this is at least 1, and that's optimized here, and so the optimum is 1.3. So it looks a bit useless. Like I want to pick a set of vertices, and what does it mean to pick half a vertex? What should I do? So here is what the algorithm tells you. Look at all the results of the ILP. Sorry, the results of the LP. Look at every yi. If yi is larger than half, round it to 1, meaning that vi will be in your set. If yi is smaller than half, then vi is not in your set. You like truncate it to 0. So when I'll truncate them in this case, it will be, of course, that I'll take all 3 vertices, but you can guess that if it's at 0.8, 0.8, and 0.2, 0.8, 0.8, 0.2, then there is a chance that it will give me the optimal solution, which is 2. So let's make it a bit formal. Round of I is 0 if y is smaller than half. Round of y is 1 if y is larger than half. Claim, look at the vertices that are larger than half, with yi larger than half. I want to convince you that this is a vertex cover. Every edge is hit. How come? Why is every edge is hit? Why can't this vertex be 0.2? This vertex will have 0.2, both smaller than half, and neither v2 nor v3 are picked.
They don't add up to 1.
Because I sum up both of them, and for every edge I require that this plus this is at least 1, implying that at least one of these two must be more than half. So when I look at this approximation, every edge is picked. Now, do I know that it's optimum? Probably not, because otherwise P equal NP and it'll be very famous. But can I guarantee something? Like it's a solution, and there is a solution to the ILP. If I would solve the ILP instead, I would find the optimum solution that minimizes the cost of everything. I don't find the optimum solution, but I guarantee that I'm not paying more than twice the optimum. That's why, because the cost of the approximated solution is what? For all the vertices in the world, sum up the rounded value of yi, times the cost that it costs. If I have a vertex that costs 100 and it got 0.6 as its yi, then I take it and I pay wi. If it's less than half, I don't pay this wi. So that would be exactly the cost of the approximated solution. The vertices that got more than half times 1. Now, what is wi times the rounded value of yi? It's at most tau 2 times wi times yi. How comes? Because if yi was less than half, then why is this true? Because if yi is less than half, then I push it down. I push it up only if yi is more than half, meaning that I at most double it. But the gap from 0.6 to 2 is obtained by multiplied by less than half. The gap from 0.3 to 1 is more than half, but 0.3 is not pushed up, it's pushed down. Everybody buys it? Round of yi would be at most twice its value, so wi times round of yi is at most twice yi. So sum of round I times wi, which is less than 2 times sum of yi wi, which is 2 times 2 from here, the optimum solution for the float, the LP solution. But what is cheaper, the solution to the LP or the solution to the ILP? Easy. The solution to the LP is smaller because it has less constraints. It doesn't feel the need to be integer. ILP has more constraints, must be integers. So this is smaller than what I would get. The opt of the float is smaller than what I'll get for the opt of the integers. But the opt of the integer is a solution to the whole problem. I think that it's very cute. So the LP helps me get good approximation using what we call LP relaxation. The LP, even though it doesn't have optimum solution, you can massage the value to give you something that is not very far from the optimum. Cutting stocks. Yet another application of LP. These are stocks, pieces of wood that you buy at Ace, Home Depot, etc. And let's assume that the length of each one of them is a and I don't know if for me this gap didn't make sense. Let's say that board is like a shelf, some piece that I need to cut from it. And the stock itself is the original piece, what I bought at length of 15. And stock will be, that's a stock, and a board is something that I cut from the board. So since I'll get confused, only the longer is what I bought, which is a stock, and a piece of it would be a board. Maybe in the next slide I called it a shelf. I don't remember which version of the slide. I'm looking at, because I used a slightly older version because it didn't download quick enough. So I want to go and buy a piece of stocks, and what I got an order for is to generate 80 pieces of 4-foot length shelves. Need to generate 80 shelves, 80 boards. Each one is of length 4. I also have one order of 50 pieces, each is of piece of length 6, and 100 pieces, each is of length 7. So here is an example of one such stock. Its length is 15 feet, and I wonder how can I generate out of it a few boards, a few pieces. And the pieces that I can generate is either of length 4 or 6 or 7. So I have a few options. And of course, when I have the order of these 80 pieces of boards, I don't need to necessarily take them from the same stocks. That's impossible, or from the same board. I need to generate the 80 pieces of 4, no matter how. So let's look at this piece of 4, and let's see how can I cut it so it's either from 4 or from 6 or from 7. Option 1, cut it into one piece of 4, another piece of 4, another piece of 4, and now I have a leftover of 3 feet of stock that is useful for these purposes. I cannot squeeze another piece of 4 out of it. So if that's a pattern that I cut a stock by into 3 pieces of 4, I'll call it plan 1. So plan 1, the first column here, consists of 3, meaning that I'll generate 3 pieces of 4, 0 pieces of 6, and 0 pieces of 7. And that's legit. It's, of course, the 3 pieces are of the desired length. Here's another option to cut it into legit pieces. 4, 4, and 7. 4, 4, and 7 also legit. So 2 pieces of, 4, 4, and 6 is also legit. So 2 times 4 plus 1 times 6, giving me less than 15. And I cannot squeeze any more piece because I just have revenue leftover of 1 unit. So this is what we'll call plan 5. Plan 5, take one stock and break it into 2 pieces of, each row refers to how many units of a 4-foot board I'm getting. Second row, how many units of 6-foot board. Plan 7 is how many units of 7-foot board. And here are all the, going over all the rows gives me all the possible ways to cut the stocks into legit pieces. And how many pieces do I get? Xi now, it's not, is an integer, but it's not between 0 and 1. Xi will tell me how many many pieces am I going to cut using plan I. Xi, does it written anywhere? Xi, the number of stocks cut according to pattern. Pattern, remember, which column? Pattern I. X1 will say how many stocks are cut according to pattern 1. X6, X5, how many units are cut according to pattern 5. I'm paying $1 per every stock, so what I'm minimizing is X1 plus X2 plus X3 plus X5. this is how many units of pattern of stocks I need to buy. Right? Ace, how the store that I bought it from doesn't care how I'm going to cut it. It just care about how many stocks did I order, and the XIs, sum up all the XIs, is exactly how many units did you order. But you need to order enough so you can fulfill this constraint. So what is xi times m1? The one here says it's row 1 times I. Let's write this expression exactly for this example. So sigma xi m1 comma I will goes, I have 6 patterns here. Just write it explicitly. It would be x1 times 3 plus x2 times 0 plus x3 times 2 plus x4 times 2. And that's it. So that is what sigma xi's mi. And what does this number, this rows, tells me? That if I cut the stocks based on x1 stocks, I cut according to pattern 1. x2 is how many I cut according to pattern 2, all the way to pattern 6. That was how many boards of length 4, how many shelves of length 4 do I get out of all this cut? Right? Because if I cut according to pattern 1, then from every one that I cut according to pattern 1, I'm getting 3 pieces. That's 3 that you see over here. If I'm cutting according to pattern 4, then I'm getting only 2 of them. Similarly, for the same XIs, that tells me how many units I get according to pattern, according to the same set of patterns, that tells me how many lengths have of length 6. How many units of length 6 do I get? Take this row, multiply by x1 dot x6. That will tell you how many units of length 6. Length 7. What's my constraint? I need to supply 80 shelves of length 4, 50 of length 6, 70 of length 7. That's my input. And now, sorry? This should be 100. You're absolutely right. Yeah. Thanks. Everybody good? Solve the ILP, and you have the optimal usage of how much you need to build. Sorry, lots of constants and maybe less cool than the other problems, but practically sounds very believable problems, very non-artificial. And that's why ILP are so much useful, and usually you'll study much more of them if you're studying industrial engineering, for example, or management information. Industrial engineering would stop.
It's not MD1, is it? The other one is MD1.
Well, because of the integers, it is. If I'll drop the integer constraint, then it will be, but then I might have some x½ ones. So of course I can solve it using the LP instead of the ILP, and who cares that maybe if the length of one board is not so bad, then it's good enough. Now, what happens if I have more boards? Then suddenly the number of columns becomes exponential. And just to make a note into it, if the number of columns depending exponential, then maybe I don't need all the columns ahead of time. And there is a technique called column generation, Write it down. It's sometimes called column generation. Sometimes it's called separating hyperplanes technique that says, hey, there is exponentially many columns here because there is so many patterns. Just generate subset of them. Maybe you're sufficient, and maybe it's not optimal and you need to add more columns. So the algorithm will tell you how I can add more columns if the columns that I generated so far don't give me the optimum solution. It's a very cool algorithm. We actually use it in some different contexts. Like we used it when in the context of art gallery, when we want to say, hey, every sensor have a battery associated with this, and I want to synchronize between them. So there is exponentially many combination of sensors in the art gallery, but we don't need all the exponential combination. We have an oracle that tells us, here are a few combinations, and either you're in optimal, and to know that it's optimal, we are using something very cool for linear programming called primal and dual problems. If I have a dual solution to the dual linear programming, and they match each other, it means that I'm optimal. If I don't have or if there is a gap in between them, I'm not in the optimum yet. So it's like a magic that spits out. You need more columns, and here is one column that if you use, will help you. Extremely cool technique, but not in this course. Thank you. And Thursday, we don't meet.